Today we're going to talk about electric potential energy. You will recall that the electric force, F equals K, Q1, Q2 over R squared, can be simplified as being Q times the electric field. Here we have two charged plates, one of them positive, the other one negative. So the electric field lines go away from the positive plate towards the negative plate. If we were to take an electron and place it down near the negative one, it would want to move against the field lines and head towards the positive charges. This means that as it moves up, it would gain velocity and therefore gain kinetic energy. So what's going on when it's right down here? Energy cannot be created or destroyed, so there must be something that got turned into kinetic energy. Any electric field has the potential to move another charge, thus giving it kinetic energy. We call this the electric potential energy, or U sub electric for short. You might recall the formula for work, which is the magnitude of the force times the magnitude of the displacement times cosine of the angle between the two. Now work has to be done in order to move a negative charge close to the negative plate. We have to give it potential energy. That means we have the electric force times some change in distance times cosine of the angle between them. When you simplify all this, you get K, Q1, Q2 over R with a negative sign because the electric force wants to push it away and we're pushing it towards. So the distance and the force are acting in opposite directions. And this gives us the equation for electric potential energy. Or another way of thinking of it is you have negative Q, the test charge or charge you brought in, times the electric field times the distance you had to drag it across. So if we know the electric field, it's actually easier to calculate it this way. This quantity here is equal to K some charge over R. Keep in mind that this is a result of the charges creating a field, not the test charge we brought in to feel the force. Because of this, it comes up so often, we give it another name. It's called the electric potential. Not potential energy, potential. This comes up so much, we actually gave it a new symbol, a capital V, or otherwise known as voltage. So the electric potential is KQ over R. If we change our electric potential, or a change in potential, change in voltage, that's the same as saying a change in potential energy over the charge. In other words, the change in electric potential is what a charge Q would experience in potential energy change. Another way of writing this, which is much more convenient, is negative the electric field times the distance that the charge moved. So here we have the change in potential, the electric potential energy, which sound very similar but are different things. Let's say we have a small little electron. Now this electron is stuck in an electric field, so it'll move a certain distance. If we know the strength of the E field, let's say, for example, 3 times 10 to the third newtons per coulomb, and we know that the electron moves a giant amount of 10 centimeters, which is 0.10 meters. We also know that the work is going to be equal to the change in potential energy in this case, which will be how much kinetic energy the electron picked up, or charge of the electron times the electric field times the change in distance. So plugging in some numbers, we have 1.6 times 10 to the minus 19 coulombs times 3 times 10 to the third newtons per coulomb times 0.10 meters. So the coulombs cancel out, leaving us with Newton meters, which is equivalent to joules. Plug in the numbers, and you get a 4.8 times 10 to the minus 17 joules. If we wanted to figure out the final velocity, we just have to equate that to the kinetic energy equation. So 1/2 mass of the electron times velocity squared equals 4.8 times 10 to the negative 17 joules. So V squared is equal to 2 times 4.8 times 10 to the minus 17 all over the mass of the electron. Now we're using some big numbers, so make sure you use your order of operations. The mass of the electron is very small. So 9.1 times 10 to the minus 31 kilograms. If you plug all this in, you get approximately 1.1 times 10 to the 7 meters per second, which is crazy fast. But electrons are very small, and that is a very strong electric field. Of course, you can combine this with your earlier knowledge of kinematics and forces to figure out the acceleration, the change in distance, the change in velocity, the force. All the units that you've learned so far are interconnected here. So don't be afraid to look into your past work to find the answers to current problems.